Okay, let's get going. Some other people show up. I want to start by talking about the first problem on the homework. I'll put up the rest of the answer key after class today. But the first part of the first problem was, why did, doing 6 binomials not really make sense for different groups of people, and there are potentially a number of ways in which that was not probably the best choice, but among which is, you have to be able to say, okay, in a binomial or even in a multinomial distribution, here's n, the total number of things that are subject to whatever it is that you're talking about. And if you're doing binomial or multinomial, they have to, the individual buckets, whether it's success or failure or like small, medium, or large or whatever, have to be mutually exclusive, exhaustive, add up to that total. And what we have in the paper that was used for the first problem in the homework, a situation in which they were using the same n, number of white people in a county or whatever, as the size of the binomial distribution for both the probability of being shot armed and being shot unarmed. And obviously, those don't form independent, mutually exclusive, and exhaustive partitions of all white people in the county. So if you were going to do the number of white people shot armed as one of your binomial things, you would need as the size the number of white people who tend to carry around weapons. And that is not something that we have reliable data on, especially compared to census data on number of white people living in a particular county, which, from the census is about as reliable as anything that we can get in the social sciences. And so it would have made more sense to do along the lines of what actually we did in the homework, is go from binomials to trinomials or multinomials with 3 categories. And so among white people, you can have shot armed, shot unarmed, or the vast majority not shot. And that forms a mutually exclusive and exhaustive partition of people of a particular racial group in that county. And so then you are, set up to use, appropriate multinomial distribution. But in this case, and in a lot of cases that you see in the social sciences, one of the most common mistakes is with these binomial, multinomial likelihoods or whatever, is either taking the total size to be an exogenous known when it's not an exogenous known. It's something that you would want to model, or like the total number of possibilities depends on the underlying probability. So that's one form of a mistake that you see a lot. And then another one is, basically, okay, doing a binomial or a multinomial, but the thing that you condition on isn't the sort of result of a mutually exclusive and exhaustive union of subgroups. It's, something else. So those are a couple of the mistakes that you see a lot in observational data when using binomial or multinomial likelihoods. So that's that. And then the next question was about, writing stand functions that you can use to draw from the prior distribution of relative risk, which was one of the main posterior quantities of interest that the authors wanted to emphasize in their paper, which is fine. But if you're going to do that, you should understand what the priors imply for that measurement thing that you want, the unknown that you want to get the posterior distribution of. And so this is an important problem to be able to do well. In order to do it, we're first going to need to grab the function or the lines of the function to draw from a bivariate normal random or bivariate normal distribution. So draw two of those. We had a function that basically was already written from week 5. To do that, all you need to do is like change it so that it only returns like one draw of two random variables rather than S, or you can just call it with S equal 1. It doesn't really matter, but get something along those lines, okay? And then we want to draw from the prior distribution of relative risk, and so that's going to have S rows, one for each simulation that we want to do from a prior distribution, and columns, one for each county that potentially could be in your data set. So as usual, we loop over the number of simulations that we want to do, capital S, and then interior to that, we loop over N, the number of observations that we have. First, at the top of this loop, we're going to draw from the prior distribution of the like country level for the United States as a whole parameters. Those are the 5 arguments that are going to go into our bivariate normal distributions, namely mu for white and non-white people once you sort of simplify it down from 3 racial categories to 2, sigma for white people and non-white people, and rho, which is the correlation between those two. It was, laid out in the appendix of the paper what priors were used for those values. They're basically normal distributions that were quite negative for the mu's. Sigma were half Cauchy with a scale of 5, so tolerating very large values for those standard deviations, and uniform between -1 and 1 on this correlation, which, okay, that's what they said in the paper, whatever, but probably could have gone with tighter priors on, a number of those things. Unlikely to have a negative correlation, I would think. So you might constrain that to be between between 0 and 1, or like -0.1 and 1, something like that. Certainly had heavy-tailed priors on those sigmas, etc. So okay, that's the stated priors for the parameters for the country as a whole. And then within each county, there's additional unknowns, namely the intercepts in these multinomial logit models. There's no predictors in this model. There's basically just intercepts. So the 3 things are the sort of intercept for being shot unarmed, the intercept to being shot armed, and fixing at 0 for identification purposes, because you could shift all of those by a constant, not change any of the probabilities. The last thing to 0, which is the intercept for not being shot. We want to do that both for armed people and unarmed people, passing in mu white, mu non-white, sigma non-white, and rho, etc. So have independent draws from this bivariate normal distribution for armed and unarmed, but correlated across the 2 racial groups. And then we want to form 2 simplexes by calling the softmax function twice. One with the armed one and unarmed one, and 0 for people who are white. Armed 2, unarmed 2, and 0 for people who are non-white. Get 2 simplexes of probabilities, and then the relative risk ratio of interest. You can define lots of relative risk ratios. All you need is 2 probabilities, and you can make a relative risk ratio. But the relative risk ratio of primary interest in this paper is the probability of being shot unarmed if you're non-white relative to the probability of being shot unarmed if you are white. So we stick that in the sth row, nth column of our matrix of priors. When we're done with both loops, we return it out. Once we get all the semicolons and stuff in the right place, we can expose it to R. We can call it, and we can visualize or otherwise investigate what does the priors assumed here imply for the prior distribution of relative risk in this respect before we condition on the data and get updated beliefs about that variable. So questions about this function? Yes?
So what is the model for the multivariate? So I can use the interactive to represent the number of the white on R or
So what do you mean by what is the model? Like
so
what's
for
the
logistic model? What is the right?
Right. In this, it's basically assuming that at each county, there's a multinomial distribution. So let's say there's 10,000 white people or 100,000, whatever, in that county. Okay, a small portion of them are going to be shot armed. Small, maybe 0 portion of them are going to be shot unarmed, and then like almost all of them not shot. Right. So we want to get the probability using the softmax transformation of each of those things, and then when we go and observe data, then it's going to be a multinomial likelihood with this construction for the probability. So it's just, well, the paper used binomial, but if we were doing it our way, we would use multinomial with 3 categories rather than 2. But I think that may not answer your question.
Yeah. I think for the multinomial model, for the left part is log I1 times 3, or we need first to choose a reference category. Maybe if we choose pi1 as a reference, if we have 3 categories, then we have 2 models, right?
Right.
So for this one, so I'm not quite understand. It's why the intercept is equals to a number of people if we use a model to interpret this kind of.
Yeah. So you could switch things around so that like the first category was the reference category and get everything to come out the same, but the priors would be different. And so the main thing here is having these like mu whites be highly negative. That's compared to 0. So if you made like the first category the reference category, then you would reinterpret the intercepts as sort of like relating to the log odds of being shot relative to being shot while armed, which is kind of a harder thing to think about, but you could reformulate the model that way. So all of this stuff is relative to the category you fix. But in principle, you could change the reference category and change around all the priors so it would have all the same implications. And then you could condition on the data and you get out the same results. So basically choosing which reference category to fix is not like a mathematical consideration. It's what allows you to think about the priors in the easiest fashion. And so it's basically saying, okay, if the intercept for being not shot, which it applies to most people, is 0, then in relative terms, how do we get an intercept for the log odds of being shot, either armed or unarmed? And so that's 3, maybe 4 standard deviations away from the reference category here, because it doesn't really happen all that often. Although when it does, it certainly on the news and stuff these days. So you could formulate it either way, but this is probably the easiest way, and this is the way that's closest to what was done in the actual paper, which was just these binomials. So in that case, like being shot was the first category and being not shot was the second category, done in like 6 different ways depending on what group of people you're talking about.
And the part I'm confused is that from the formula, we can see that the intercept is a log of the number.
Yes.
But here we just use the intercept as a number.
It is still in terms of log. So remember, softmax is equal to, you know, E of like shot armed, you know, E of shot armed plus E shot unarmed plus E not. And so that gives you back the probability of being shot armed, and you can do the same thing for the other two. So this, these are real numbers. They're not counts, but they don't have a simple relationship to the probability because it depends on all 3 in the denominator. And that's among the reasons why we have to fix one of them. So this is a classic example of like what you put the prior on is not exactly the thing that you care about, which is the probability or the ratio of probabilities. But that's sort of just the way they do the model. So we need to be able to put priors on these unrestricted things and then evaluate what they imply for simplexes or other sorts of constrained things. Anyway, this is the probability, and you could get the other 5 probabilities the same way. And then, you know, if you have the data, which I guess you could get, you could condition on those and then update your beliefs about all this stuff. Other questions? So, I mean, this is something that you've got to be able to do, and you've got to be able to practice until you could do it well. So, I mean, there's a number of things that are kind of suspect about how this paper chose to estimate its thing, but at least it explained what it is that it did in the appendix, which is often a lot more information than you get out of a lot of papers that don't have a complete explanation for what they did. Now, it was relegated to an appendix as far like it was published in some journal of anthropology, which, you know, okay, there's a lot of different like fields that study police stuff, but it could have just as well appeared in a public policy journal or an econ journal, I guess, or something like that. But anyway, my impression is, without having really read very much, that there's probably not a lot of empirical Bayesian sorts of papers appearing in a journal like that. And so it's like kind of sad, but not really surprising that you could read the whole main text of the paper and not even really know that this is a Bayesian approach. But at least in the appendix, they explain, you know, all the distributions and the stuff that they did. And so if that information is there, and sometimes even when it isn't, you need to be able to like translate it into code. So as I was saying last time, there's really only one sufficient condition to say that you really understand the model, and that's if you can represent that model in code, because that's really what models are. They're like these simplifications of reality that, you know, we think are faithful enough to the reality that's going on, but that are simple enough that we can understand, like, if you like change this or change that, you know, what would be the implications? How would it change the predictions for the observables and whatnot? So, you know, a lot of people say, okay, you know, I understand this model, but just, you know, would read like the abstract and the conclusion and like glance at the tables and be like, okay, it's like a paper about police shootings, you know, I understand it. But they don't really understand the model on a deeper level. And even if they did, you know, scrutinize the appendix, you can't really demonstrate that you understand the model unless you can reduce it to code. And so a lot of times you'll find that, if you don't take that step of trying to encode the model, that you don't really understand it. But even if you do, that you still have to be able to write it in code, not necessarily the Stan language, but you might as well, in order to go farther. So how can you assess whether the priors that they use on these parameters are reasonable unless you can see what those priors imply for observables, like proportion of people shot this racial category, that racial category, armed, unarmed, etc. You have to be able to push your beliefs about all of these unknown parameters through the model in order to get predictions of observables on the outside that you can then use to assess whether the prior that you are using were reasonable. So in this case, the relative risk ratio is going to have a median of 1 because you're drawing both the numerator and the denominator from the same marginal distributions, but it's going to have like a heavy tail because anytime you have ratios, that's usually going to go on. But you could look at that and say, okay, that's sort of a reasonable distribution of beliefs or not, in which case you could go back and change it. And that's the other part of this, why you need to be able to encode models is, okay, let's say you've figured out with this model and you think you disagree with some aspect of it, you want to change it. In order to be able to change it, you have to be able to build it in the first place. And there's a lot of things out there where people will write one paper responding to another paper, and they'll build this like alternative model, but they didn't take the time to build or encode the model of the paper that they're criticizing. And so there's like some slippage where what they think the model they're criticizing is not actually the model that was being specified in the paper, although the model in the original paper may have been specified with insufficient amount of detail, and so it could be kind of both their faults. But for like a number of reasons, demonstrating that you understand the model, being able to assess whether the priors are reasonable, being able to assess whether this is a model that Stan can draw from the posterior distribution of well. We haven't really talked about that much, but we will later on in April. The way in which we can establish that Stan is working is by drawing from the prior predictive distribution, conditioning on that data, and then seeing if we get basically our prior distribution back, and doing that over and over again. That's how we can establish that our software is working well enough for data like this in order to go out and collect data from the wild and then condition on, which entails the additional possibility that the data from the wild weren't generated by the same process, but assuming it was, and assuming you've established Stan can handle that process, then you can have, pretty much good assurances that Stan will work well, which in general, we can't, not for all situations and all data sets that you could come up with in all prior distributions that you could use. There's just like way too many of those for us to be able to say like, in general, Stan is gonna work. But in particular, cases, if you draw from the prior predictive distribution and then use that condition on that, you should basically get your priors back. And that is something that you can assess. So understanding the model, assessing whether the priors are reasonable, assessing whether Stan is going to be able to handle this posterior distribution well, and then putting yourself in a position, okay, now that you understand what model somebody else did or implied, then what do we change? What do you want to change? What do you want to change in order to produce new research? And so for all those reasons, you have to be able to encode the model rather than just skip to the step where you like estimate logic coefficients or things like that. So I think we had, Too many people giving up on something like this. Too many people spending, too much time writing a function that's, like all the other functions we've written, like 20 lines. Well, it'd be like 30, but a third of them are already we had in week 5. So once you have a good understanding of what's the paper is talking about, then putting it into like these 20 lines or whatever shouldn't really be taking days and days and days to do. But it can take a long time if you haven't had enough practice doing it. And so we just got to keep practicing these things, even though we have things like RSNARM and BRMS that can get posterior distributions for us. We still want to be able to at least write the priors using the stand language directly ourselves. Questions more about that? Yeah. So then, the one after that, about the county level model, you could estimate what that would stand GLM. There's some, problems with taking the logarithm of 0 and some stuff like that, but I guess most people got around that. And you probably found that, like, if you plug it into ProjPred and go through that process, that there's like a model with 1 or 2 predictors that would be expected to predict this relative risk ratio thing. Just as well as the 25th model of all the ones that they estimated. And so that would probably be a better approach in a situation like this, although not really the best approach, because taking posterior means from one model and then modeling them with another Bayesian thing, it means you've done it wrong. It seems sort of intuitive to a lot of people, but really the right thing to do is combine both parts of the model, in which case all this like county variables of like number of assaults and stuff like that would go into your prior on these thetas. And so combining those together makes better use of the information. It's also like valid usage of probabilities. So you really wouldn't do this in 2 steps. But that's what the original paper did, and that gives us opportunity to use like StanGLM and Varcel and stuff like that. But what you find in a lot of these situations in which people don't have like exactly a well thought out theoretical model for something like this in the social sciences is just sort of throwing a lot of census level data at something, is that there's a tendency to overfit. There's also, you can get a lot of observations sort of and not accumulate a whole lot of information about the parameters of interest. So, part of the problem with this line of research is for like decades and decades and decades, no one even really collected data on how many people were shot by the police. And it took like a journalist to start like crowdsourcing this thing to, start to put together a dependent variable like this that researchers could use, because like the federal crime reports and stuff like that don't include people shot by police. So, okay, there's a lot of effort that went into going to collect the data, but it's still a relatively rare phenomenon, and there's not a whole lot of information with which to draw precise posterior distributions about these unknowns. So when facing that situation, you need to make best use of the information that you have, and that means combining parts of the models together rather than estimating them in 2 steps, which is never a right thing to do from a Bayesian perspective. But it also means you may have to limit yourself to relatively simple models, because you don't have this overwhelming amount of information with which you can precisely estimate the parameters of more complicated models, which may actually represent the truth, but there's no real utility of estimating a complicated rich model if you don't have rich data that provide a lot of information about the parameters. But it's sometimes hard to know like how complicated a model you can afford to estimate from the outset. And so definitely a reasonable approach would be, to start with the variables that you have and use projection pursuit in order to pare it down afterwards, which you can often do substantially to get a model that doesn't necessarily mean it's right. Indeed, there's no way to tell, but it is expected to predict future data on shootings, at least as well as a much more complicated model, but doing it with like 1 or 2 predictors, maybe. So questions about the first problem? Yeah, second problem, I mean, different people can do different things there. You just need to do something reasonable with the ordinal outcome variable, of which there's plenty to choose from. So hopefully we have much trouble with that. Okay, so turning now to what we have for today. All right, so talking more about multivariate probability after we disclose the fact that working at Columbia and working with something that Columbia seeks grants to develop creates the appearance of a conflict of interest that you should be aware of, even though I think I'm not exactly talking about anything particular to stand today. Just talking about math, particularly the math associated with multivariate probability. And this definitely builds on this stuff about univariate probability, particularly in the case of univariate continuous variables that we learned about in February. So now we want to think about X as a vector of random variables, a vector of size K that are continuous. So as we mentioned before, but not gone into great detail about, we can still define a multivariate CDF. The probability of x1 is less than or equal to this, x2 is less than or equal to that, xk is less than or equal to that, all of those k inequalities holding simultaneously. The probability of that is our CDF. We can then assess how does that CDF change if we make small changes to the variables in the inequalities. And so if we have this CDF that is a function of k random variables, we can differentiate that with respect to the first, with respect to the second, on with respect to the k, so-called total derivative to obtain a multivariate PDF. That multivariate PDF can always be written as a marginal univariate probability for the first thing times a conditional probability density function for the second thing given the first thing times a conditional density function for the third thing given the first two things, etc., all the way up to the conditional probability of the kth thing given everything else. And that is a telescoping factorization of the joint PDF into a marginal and a k-1 conditionals. You just got to work out what those are if necessary. Conceptually, at least, the CDF can be written by integration of the PDF from like whatever is the minimum value up to each of the little x's by integrating the PDF. You're almost never going to be able to do that integral analytically, multivariate integral, but conceptually it's still, the area in this k-dimensional space, just inverting the fundamental theorem of calculus to go from integrals to derivatives and whatnot. Another integral that you can't do, but you can sort of imagine, is what is the expectation of some function g that depends on k random variables in the x vector, and that follows from the definition of expectation that we used before. So taking that g function, weighting it by its joint PDF integrating that over all k dimensions, and you get the so-called expectation of function g, but that's another thing you're unlikely to be able to do analytically. Particular g function of interest is the identity function, in which case the expectation of x is a vector of size k, which will denote mu as usual. The expectation of a vector is a vector of expectations. You would have to do like multidimensional integration in order to obtain any of those expectations. But again, conceptually, we can think about expectation of a vector as being a vector of expectations. And moreover, we can get the sort of expectation of this function, x minus mu post multiplied by x minus mu transpose. So x minus mu is going to be k minus 1. X minus mu transpose is 1 by k. And so k by 1 times 1 by k is going to be a k by k matrix. And the expectation of that function is special enough to have its own symbol, capital sigma, which represents the variance-covariance matrix we were talking about at the end of class last time. Down the diagonals, it has variances or squared standard deviations. In the off diagonals, it has covariances between any pair of the k variables. And this matrix is symmetric, which is to say, you know, sigma 1, 2 here is the same as sigma 1, 2 there. The covariance between variable 1 and 2 is the same as the covariance between 2 and 1, and the same for all the off diagonal elements in the upper triangle. They're going to have equivalent counterpart in the lower triangle of the variance covariance matrix. So this matrix is symmetric. So like I said, you're not really going to be doing these integrals analytically, but conceptually they define the pieces for, you know, multivariate probability that are analogous to the pieces we use for univariate probability, where like at least sometimes we can do the integrals. Questions about those? Okay. So determinant. A determinant of a square matrix is a function that inputs a square matrix and outputs a scalar. It is sort of like a multivariate version of absolute value, although it can be negative. But it's denoted with the same absolute value symbol because it's like kind of the multivariate version of absolute value. As it was said in the reading, if the determinant is not 0 of a square matrix, then the inverse of that matrix exists. And the determinant of the inverse is the reciprocal of the determinant. But we don't really, you know, calculate a determinant in order to see if an inverse exists, because, you know, we can't really calculate things with exact numerical accuracy on a computer. So we can never really tell if it's exactly 0 or just like real close to 0. So we don't really use the determinant to tell if the inverse exists. It either exists by construction, or by construction it doesn't exist. So we do have to calculate these determinants sometimes. It's best avoided if possible, but you sometimes can't avoid it. So here's all you need to know about how a computer calculates determinant. One, determinants are only defined for square matrices, so in general. So we're only talking about square matrices. And any square matrix can be factored as the product of two square matrices, L and U. L is unit lower triangular, which is to say all its upper triangle elements are 0. That makes it upper triangle, lower triangle. But it's unit lower triangular, which means all its elements along the diagonal are 1. So L times U, and U is upper triangular with unrestricted diagonal elements, but everything in the lower triangle being 0. And, you know, for covariance matrices like sigma, there's like some even more simplifications that you can do. But this applies to any square matrix X, whether it's a covariance matrix or not, whether it's symmetric or asymmetric. Any square matrix can be written as the product of two triangular matrices. This is the so-called LU decomposition. and the determinant of a product of square matrices is equal to the product of the determinants. So the determinant of X is equal to the determinant of L times the determinant of U. And determinants of triangular matrices are the product of their triangular elements. Thus, we can write the determinant of X as the determinant of L times the determinant of U, but L is unit lower triangular, which means all its diagonal elements are 1. The product of K1s is just 1. So the determinant of X is actually equal to the determinant of U, the product down the diagonal of the U upper triangular matrix. And so that, when you call det in R or determinant in stan, that's what it's doing to calculate the determinant of X, first factoring it and then calculating the determinant of the U matrix. So that's another instance in which matrix factorization makes our lives easier, even though it sort of creates two matrices where there used to be just one. The two matrices have special structure to them, which makes calculations relatively simple. Just multiply down the diagonal. Anyway, so all functions for all software for dealing with linear algebra is going to have a determinant function that you can call, but that's just kind of what it's doing on the inside. So what are determinants used for? So like I said, we're never going to be able to really do those integrals that define a multivariate CDF. The way most multivariate distributions are created is by first specifying some distribution that we're going to take like independent random draws from, and then transforming those K independent variables in some way that makes them K dependent variables, and working out what is the PDF for the joint distribution of those dependent variables. And this goes a little something like this. So if you have a random vector Z that has some PDF, and then X is a bijective function of Z, so a mapping from all K elements of Z to all K elements of X that is invertible. What's the PDF of X? So we've done this problem a number of times with univariate random variables like log normal and stuff like that. But here's how we do it for multivariate random variables. It's the same principles, just more complicated. So the PDF for X is going to be, okay, we differentiate the CDF of Z K times, or we take the total derivative of that. And then we multiply it by all the chain rules involved for the whatever is the transformation from X to Z. But you can have things like, okay, the second Z variable affects the first X variable. And so there's a lot of chain rule stuff going on. And that can be written in a relatively simple fashion by saying, okay, we're going to evaluate the PDF of Z written in terms of X and multiply by the determinant of the so-called Jacobian matrix, named for Jacob Bernoulli, who also invented the Bernoulli distribution. And so a Jacobian matrix is just a matrix of first derivatives that are organized into rows and columns. So the thing in the top left is the derivative of Z1 with respect to X1. Next to it is the derivative of Z1 with respect to X2. Below that is the derivative of Z2 with respect to X1. Next to that, Z2, X2, etc. Filling up the whole K by K matrix with K squared partial derivatives, the derivative of one of the outputs with respect to any one of the inputs. So if we organize those into a square matrix J, called the Jacobian matrix, the determinant of that matrix is what we need to multiply the PDF of Z by, written in terms of X, in order to make this a valid PDF for X, which is to say conceptually it integrates to 1 over whatever the parameter space or sample space of X is. And we've done this a bunch of times for univariate distributions, which you can just think it's the same thing with K equal 1 variables, in which case the determinant of a 1-by-1 matrix is just like whatever is the absolute value of that derivative. which we've done before. I don't know if I said like do the absolute value. I think we only did positive increasing transformations, but in general, you take the univariate PDF and you multiply by the absolute value of the derivative. I just think all the ones we did so far were positive, but that ensures that your PDF is a non-negative function rather than a negative function, which wouldn't make sense. So this business about multiplying by the determinant of a Jacobian matrix is really just the generalization of what we learned before, univariate variables doing change of variables like that. So rather than just sort of keep it abstract, let's work through an example of this in like the k equal 2 dimensional case. So let's say we have a matrix L that looks like this. It has some standard deviations and a correlation in different ways in it. And let's say Z1 and Z2 are two independent random variables that are standard normal and independent of each other. And so we're going to put those into a vector. And then we'll define the vector of size 2 x as mu, which is another vector of size 2, plus L post-multiplied by the vector z. And then we want to ask ourselves the question, okay, if z is distributed independent standard normal elements of that, what's going to be the distribution of x when we do this transformation? So if we write this out in terms of scalars, x1 is equal to mu1 plus L11 times z1 plus L12, which is 0, times z2. So 0 times z2 is just 0, leaving us with mu1 plus sigma 1 times z1. And x2 is equal to mu2 plus rho times sigma 2 times z1 plus sigma 2 times the square root of 1 minus rho squared times z2, which is what we have here. Okay, if that's x is a function of z, how do we reverse this around to get z as a function of x? So this is pretty simple for z1. It's just take x, subtract u1, and divide by sigma 1. Now you've isolated z1. Slightly harder in the case of z2. So you have x, subtract mu2, subtract rho times sigma 2 times z1, and then divide by sigma 2, 1 minus rho squared, the square root of that. But we know z1 already is equal to x1 minus v1 divided by sigma 1. So we write that in the bottom here. We find that z2 is equal to x2 minus mu2 minus rho times sigma 2 times z1 in the form of x, and then divided by sigma 2 square root 1 minus rho squared. So just algebra there, but I'm doing it in terms of scalars, or well, I'm showing it in terms of the scalars that are contained within the vectors and whatnot. So anyway, just take my word for it that that is z written as a function of x. Okay, so we have z. We know z is distributed independently standard normal. We have it written in terms of x. How do we now get the PDF for x now that we've inverted our transformation? Okay, we're going to need to fill in the elements of the Jacobian matrix, which holds the 2 by 2 partial derivatives. So first, what's the derivative of z1 with respect to x1? That's just going to be 1 over sigma 1. So we put that there. Derivative of z2 over x1 is this, which turns out to not really matter. Derivative of z1 with respect to x2. So x2 doesn't appear in the expression for z1. So that's just going to be 0. And then derivative of z2 with respect to x2 is just 1 over sigma 2 times 1 minus rho squared. So we get a Jacobian matrix that is lower triangular. The determinant of a lower triangular matrix is the product down the diagonal. So the determinant of this matrix is going to be 1 over sigma 1 times sigma 2 times the square root of 1 minus rho squared. And so now we have our Jacobian. We can multiply that by the PDF for z written in terms of x. So that was independent standard normal. So we just take the two independent standard normals for Z, substitute our expressions for those, so they're written in terms of x1 and x2, wherever we had z1 and z2 in the bivariate but independent standard normals, and then multiply by the Jacobian, rearrange things a little bit, and we see we get the same form as the bivariate normal PDF that we've been working with before, where we have a marginal PDF for x and a conditional PDF for marginal PDF for x1 and a conditional PDF for x1 given, or x2 given x1, that has a different conditional mean and a different conditional standard deviation, but is still a normal distribution. And so here we basically use the linear algebra version to obtain the bivariate normal PDF, but using vectors and matrices rather than, before we just sort of asserted it and or, worked it out just with scalars. But the reason why we want to see this in terms of matrices and vectors is we can generalize this from bivariate normal to trivariate normal to multivariate normal. So, we talked several weeks ago, how do we draw from like a standard normal, okay, like inverse CDF method, whatever. How do we go from standard normal to general normal? Well, we multiply standard normal by sigma, shift it over by mu. Now we have something that's distributed normal with mean mu and standard deviation sigma, but it's just univariate. So how can we go from univariate normal to bivariate normal? Well, we take a marginal univariate normal and multiply it by a conditional normal given, the first one. Okay, now we're in bivariate normal territory. We've used that on the homework. How do we go from bivariate normal to multivariate normal with the arbitrary number of random variables in it, which is really what the paper on the homework was actually doing, but we hadn't learned about multivariate for the intercepts. We haven't learned about multivariate normal yet, so we had to sort of restrict ourselves to bivariate normal, which may have actually been better, but it is still a restriction that we don't want to be burdened with for the rest of the semester. So now let's try to figure out how can we derive where the multivariate normal distribution comes from four arbitrary values of k. So if we have z as being independent standard normals, all k of them, and x written as a function of z is mu plus L times Z, where L is a lower triangular matrix with positive diagonal elements. So the same as what we had before, it's just it doesn't have to be restricted to be 2 by 2. It can be any k by k lower triangular matrix with positive diagonal elements to it. And so x is equal to mu plus L times Z. How can we flip this around and figure out what is the distribution of x if z is independent standard normal in this transformation? Now proceeds by the following steps. First, we invert the transformation to write z as a function of x. So we just subtract mu from both sides, and then we multiply both sides by L inverse in order to make L inverse times L the identity matrix. And z times the identity matrix is just z. So in order to isolate z, we subtract mu from x and then multiply on the left by L inverse. Okay, now we've inverted the transformation. L inverse is a lower triangular matrix itself. So the ith element of z as a function of x can be written as the sum from 1 to I of x, that should be k, I guess, or that should be j, really. Whatever. The previous values of x minus their expectations multiplied by the respective off-diagonal elements of L, and then one diagonal element. Okay, so that is the relationship for any one scalar in Z as a function of x. Okay, so what are the derivatives of that? Well, the derivative of zi with respect to xj is just going to be the ij element of the inverse matrix of L, and that's true for all I and j. So the Jacobian matrix is just L inverse in this case, which is a lower triangular matrix, and consequently its determinant can be written as the product of the triangular elements, and so it's just going to be 1 over the determinant of L is going to be a determinant of the Jacobian matrix that we need to multiply by. So what's the PDF of X in terms of mu and L? Well, that's the PDF of Z written in terms of X multiplied by the Jacobian, which is just 1 over the determinant of L, the product down the diagonal elements of L. So we don't actually even have to form L inverse explicitly yet. So what's the PDF of Z? Well, we said they were independent standard normals. So we just multiplied the PDF of the standard normal for each of the k values. We have this product of the squares of Z. So we can write that as e raised to the power negative 1/2 times the sum of the squared z's, which we can write in vector terms as z transpose times z. So the joint distribution of these independent standard normals has this PDF, and then we want to substitute out z, write that in terms of x, which is this right here, and then or that there, and then multiply by the Jacobian, which is just 1 over the determinant of L. So we get this expression here to write this multivariate normal distribution in terms of mu and L. But that's not the most common way, although it's the best way. The parameterization talked about in the reading goes a step farther, substituting this matrix sigma for L times L transpose, in which case we can write the multivariate normal PDF with parameter mu and variance covariance matrix sigma, which is a symmetric matrix, as opposed to L, which is a lower triangular matrix, utilizing the fact that the determinant of sigma is just the square root of the determinant of L, because determinant of a product is equal to the product of the determinant. We can write the multivariate normal PDF in a more common form, even though for use in STAN, it actually turns out to be better to use this parameterization of the multivariate normal distribution. So you should be able to understand these steps, but you don't necessarily have to understand all of these steps on the first glance. But again, it's just an extension of this idea that we talked about before when we're talking about, okay, we know the distribution of one thing, and we know what transformation we want to apply to it. What's the PDF of the transformed variable? We need to invert that transformation. We need to take derivatives of that transformation. And then we need to multiply the PDF for the thing that we know by now a Jacobian determinant of derivatives, and write that thing in terms of the random variable whose distribution we want. And that's how we get PDFs for these multivariate distributions in most cases. It's not by differentiating the CDF. It's by taking independent variables from some distribution, univariate, that we know, and then collecting them together, and then applying some transformation to them to create variables that are not independent, and then working through what the PDF of these not independent k variables are. And by far the most important instance of that is the multivariate normal distribution, which is even more central to multivariate probability than the individual, the univariate normal is to univariate probability. At least there are like a bunch of other univariate probability distributions that are used. Almost all the multivariate distributions are either multivariate normal or derived or similar to in some way the multivariate normal. So it really is central for multivariate probability, and it has some important properties. So what's this matrix L that we've been using to do the transformation of independent standard normal Z's into dependent multivariate normal X's. And this is what's known as a Cholesky factor. So it's a lower triangular matrix with positive diagonal elements such that L times L transpose is a variance covariance matrix. If that's the case, we say that L is a Cholesky factor. So this is a very important matrix concept that was invented by this Cholesky guy. Apparently, like, while he was in a trench during World War I and like didn't have a whole lot else to do, so he was sketching this out on his notebook. And then he got hit with the like massive artillery thing and died, but like somebody else in his battalion or whatever like scooped up his notebook and then like gave it to somebody who would understand it, and then it got published and turned out to be like really important. But anyway, so the Cholesky factor is a function that can be written, it's bijective, so it can be written from the elements of sigma in a recursive fashion. There's functions to do this in R and Stan that have different names, but they can do them. But the main thing to see about this here is that the diagonal elements of the Cholesky factor are square roots of like this business here. And it's not self-evident that the number underneath the square root sign is going to be non-negative. Like, it could be negative, in which case the square root of it wouldn't be real. But the fact that covariance matrices are also what's known as positive definite means that all of these diagonal elements are real, which is to say the thing underneath the square root is positive. That's what positive definiteness of a matrix implies. It's a restriction on square matrices, but it's a restriction that is satisfied by all covariance matrices and covariance matrices. It implies the inverse of sigma exists and can be calculated from the Cholesky factor. The inverse of a variance covariance matrix is known as a precision matrix. So you'll see that sometimes. But anyway, not all symmetric matrices are positive definite, but almost all positive definite matrices are symmetric. And so these covariance matrices are really the parameter space that they live in is a subset of k choose 2 plus k real dimensional space. There's an inequality, multivariate inequality restriction on the elements of these variance covariance matrices that imply the diagonal elements of the Cholesky factor are real when it's like not obvious that that is true, but it is. Anyway, there's Cholesky decompose and Stan, almost like the Chol function in R, but Chol in R outputs the transpose of L. So this L that we're using to do this transformation has a special name, and it's called the Cholesky factor. And it's very important when we get to working with stuff in Stan. It's usually easier to use the Cholesky factor L than it is to use the variance covariance matrix sigma, even though you can go from one to the other. Things work better if you do it with L. So a lot of the properties of a multivariate normal can be established in a relatively simple fashion, given what we've done before. So the expectation of x is just going to be expectation of mu plus expectation of L times z. Mu and L are constants, so we can pull those out of the expectation. We're left with expectation of x being mu plus L times the expectation of z. Expectation of z is just a vector of zeros, because z is distributed independent standard normal. So we have 0 times L, which is 0, meaning the expectation of x is here. What's the variance covariance matrix of x? Well, that's E of this thing. Pull the L's out because they're constant. Expectation of z times z transpose is the identity matrix, because these standard normal random variables are independent of each other, hence they're going to be uncorrelated in the off diagonals. L times I times L transpose is L times L transpose defined as sigma. So sigma is the variance covariance matrix of the multivariate normal distribution, and its Cholesky factor is L. This all simplifies in a neat way if k is 2 to a bivariate normal, or if k is 1 to a univariate normal. So we're just generalizing this to k variate normals. We can also do what's known as partitioning vectors and matrices. So what this means here, let's say we have some random variables of size k and x. We can partition them into like 2 subvectors. So xa is like size ka and xb is size kb, and ka plus kb is equal to k. Do the same thing with mu. We have to partition sigma 2 ways. So this is basically like a 2 by 2 matrix, but each element of the matrix is a matrix. So it's like 4 matrices within a matrix. But it altogether implies a k by k matrix for both sigma and Ramel. So it can be shown, based on what we've done so far, that x sub a, which is a subset of x, is going to be multivariate normal with expectation UA, variance covariance matrix sigma, and Cholesky factor LA. Same thing for B, pretty much. So any subset of a multivariate normal distribution is marginally multivariate normal, or if it's a subset of size 1, just univariate normal. Also, the conditional distribution of xb given xa is also going to be multivariate normal, albeit with expectation that is, that function there, and variance covariance matrix, which is this function here, and the other way around for xa given xb. And so one of the reasons why people like the multivariate normal distribution and use it all the time when doing multivariate probability is, one, it's one of the few ones that we can do in a somewhat analytical fashion. But two, if you have something that's jointly multivariate normal, all the subsets of it are marginally multivariate normal. All the conditional distributions of any one group given the other group are also going to be multivariate normal. So the joint is multivariate normal. Each margin within that is multivariate normal. Each conditional distribution within that is going to be multivariate normal. So it forms a very coherent family of distributions where like everything is normal depending on whether it's joint or marginal or conditional. It's just different hyperparameter values depending on whether we're doing like a joint piece or a joint or a marginal piece or a conditional piece, whatever. So it forms a coherent family of marginal, joint, conditional, all being multivariate normal. But you might say, well, okay, if that's multivariate normal distribution, I could use it for like multivariate outputs, but how would I put priors on mu and sigma that are in the multivariate normal distribution? So if I wanted to estimate mu and sigma, I'm going to need priors on those things. How would I do that? So we go back to what we were talking about at the end of class on Tuesday, this decomposition of a variance covariance matrix into a diagonal matrix of standard deviations, delta, multiplied by a k by k correlation matrix, lambda, which is going to have ones down the diagonal, correlations in the off diagonal, and be symmetric. And then post-multiplied again by delta, the diagonal matrix of standard deviations. So we can decompose or factor a variance covariance matrix sigma into diagonal matrix of standard deviation, correlation matrix, which is symmetric and has ones on its diagonals, and diagonal matrix of standard deviations, again, on the right. So you might say, how is this easier? I used to have one matrix sigma. Now I have 2 matrices, and they're multiplied together in 3 ways. Well, it's because putting a prior on delta and lambda is easier than putting a prior on sigma. But whatever priors you have on the standard deviation and the correlation matrix imply a valid prior on sigma. It just doesn't have a name. So, okay, I kind of can understand how you put priors on standard deviations. We could use exponential or gamma or half Cauchy or whatever for those. but what prior would we put on a correlation matrix? And part of the reason why this, what I'm about to say, works pretty well is because whatever you believe about the standard deviations basically tells you no information about what you believe about the correlations. The standard deviations just give you units. So if I say like the standard deviation of this is 5, and the standard deviation of that is like 8.2, does that tell you anything about the correlation between those two things? Yeah. And so you can specify sort of independent priors on delta, independent from lambda. And putting priors on the diagonal elements of delta is not so hard. That just leaves us the question, what prior should be put on the correlation matrix lambda? And there's a family of distributions that was written in a paper by Lewandowski, Kuro, Fishka, and Joe a few years ago, back when we were first writing Stan. Except me and Bob Carpenter could never spell Lewandowski, Kuro, Fishka. We could spell Joe, but the first two others we couldn't spell. So we just shortened the name of this distribution to LKJ, which is an abbreviation for the authors. It's a distribution or a PDF for correlation matrices, where the density is proportional to the determinant of the correlation matrix raised to the power of eta minus 1, where eta is a hyperparameter that you choose. Clearly, if you set eta equal to 1, then you're raising a determinant to the power of 0, which is just going to be 1, which is to say this density is constant over the space of correlation matrices, which is a weird space, but the density is constant. And so it's entirely possible to put a uniform distribution jointly on a correlation matrix. That's different from putting uniform distributions independently on the elements of a correlation matrix, because those elements aren't independent of each other. So that's a bad idea. But we can put a jointly uniform prior on a correlation matrix, and a lot of times that's what people prefer to do. If you set eta to some value greater than 1, then the mode of this distribution for correlation matrices is going to be the identity matrix. The mean is also the identity matrix. And so a lot of times, insofar as people have prior beliefs about a correlation matrix, it might be that these variables are not super correlated, in which case having like a mode at the identity matrix makes some sense. And the bigger eta, the stronger the mode. If eta is between 0 and 1, there's like an anti-mode where the identity matrix is the least, is the correlation matrix with the least density, which is usually a weird thing to believe. It's like 0 correlations are unlikely, but correlations of like +1 and -1 are like equally likely. That's usually a weird thing to believe. So usually people are setting eta to be 1 or greater than 1, depending on whether they want a flat density or a density that has a mode at the identity matrix. You can also work through what's the distribution of a Cholesky factor of a correlation matrix. So that's available in Stan. But anyway, by using this distribution, which is fairly easy on correlation matrices, and it's relatively easy to put some positive prior on standard deviations, we can do those collectively and thereby form a valid covariance matrix sigma, and we have valid priors on the components of sigma factors. So this is another example among many where decomposing a complicated matrix into more matrices that are simpler in the sense that they have special structure that makes it easier for us to work with, like diagonal or triangular or whatever, makes it easier to specify reasonable priors on the parts. And if you can specify a prior on all the parts, you've implied a prior on the whole that's valid. But it wasn't self-evident as to how you would do that if you just sort of said, like, what prior am I going to put on sigma? Much easier to decompose. Okay, so out of time for this week. Pick it up on Tuesday. Start talking about hierarchical models, which are basically going to heavily involve the multivariate normal as a prior on all these like group level parameters. And so this sort of serves as an introduction for that. We'll be doing that in BRMS and RStanR, but also talking about the relationship between those and frequentist software, which claims to be estimating similar models, but really isn't. Okay, so that's what we have to look forward for next week.